Good morning, evening, or afternoon, seniors. Today's lesson, we're going to be talking a little bit about some of these fundamental elementary particles. Let me explain what an elementary particle is once again. So if I take a hunk of gold and I cut it in half and cut it in half, I keep getting gold, keep getting gold, keep getting gold. If I eventually get down to one atom of gold, well, that's not an elementary particle because I can cut that atom of gold and maybe get protons and neutrons that make up that atom of gold. So maybe the protons and neutrons and electrons are elementary particles. But as it turns out, the protons and the neutrons can actually be split up even further into making other things that are elementary particles. In this case, quarks and leptons and such like this. So right now, what you're seeing, quarks, leptons, and bosons, these are what we would call the elementary particles. These are the smallest bits of matter that you can have. You can't simplify things any more than this. Now, could there be some more smaller pieces of this matter that we're not unaware of? Yes, but we have not been able to find those yet. We don't have any theories behind that yet. As of now, this is the elementary particles. Now, today's lesson is we're simply going to go into naming these. I'm going to show you what we call the standard model. The standard model is the model that we've made to basically illustrate all the different quarks and leptons and bosons that have been discovered and verified. And we're going to talk about how that model is put together, and we're going to talk about various properties of these things. Going forward into next week, we're going to be taking a look at how these objects interact with each other. How do the up and the down quarks interact? What do they do? How do the leptons interact with the quarks? And understanding the properties of these is going to be very important. Be very, very crucial, and we'll get into that next week with conservation laws and Feynman diagrams and the such. So that's why this week, even though it is a lighter week as far as work, I really want to make sure you come out of this week understanding what all these particles are. The assignment for today and this week is going to be, I want you to make your own standard model. You can pull pictures off the internet and I can show you diagrams on my iPad or whatever, but I want you to make your own. I want you to make it fantastic and colorful with all the information you're going to need because, boy, we're going to be using that standard model next week. And so I want you to make your own. I want you to do a scan with your phone or take a picture of it, however works best for you. And that's going to be your grade for this week, is to make your own standard model with the information I give you. So just again to point out, we have the quarks and the leptons. The bosons are sort of different. We're going to mainly be leaving them alone today. We'll talk about what the bosons are and give you the properties, but they're sort of off on their own a little bit for now. We also have, these aren't elementary particles. These are compound particles here, but hadrons. We have two types of hadrons. We have a baryon and a meson. Baryon's 3 quarks, meson's 2 quarks, and through what we talk about today, we'll explain why it's got to be one or the other. You could have 5 quarks theoretically, but that's not something we see a whole bunch of. So let's first talk about the quarks. Quarks, I think, are the more interesting of the particles. And don't worry, in our Zoom chat, I'll show off all the little particles. They're all sitting right here. But the quarks, we always lay out the quarks like such. There are 12 quarks, but we usually only write 6. And in your little standard model that you're going to make, you're only going to put 6. And so the quarks we're going to start on the left with the up quark and the down quark, the charm quark and the strange quark, the top quark and the bottom quark. Now, if these seem like strange names to you, don't worry, you're not alone. At some point, they just had to come up with some names for these things, and this is what they call them. So these are actually the quarks that make up all living matter. Everything that we know of is made up of these little quarks. Sort of interesting. So let's talk about some properties. What are some important properties you need to know about these quarks? Trust me, there are a lot of properties of all these quarks and leptons and bosons out there. But some of these we're not going to worry about too much. For example, flavor, the color. These are all things that people use to describe the different quarks, but for the purposes of our lesson and our standards that we have to meet, we're not going to go into those. We're going to talk mainly about two main variables and another variable that sort of goes around there. The three variables are the charge, the mass, and the strangeness. The charge, the mass, and the strangeness. That seems sort of weird. Actually, I'm going to tell you, I'm going to put these in different colors so we can tell them apart. So mass will be green, and we'll have purple will be charge, and we'll have blue be strangeness. Okay. So first, let's talk about mass. Mass is pretty straightforward when you're looking at the Standard Model. On the left side, you have low mass. On the right side, you have high mass. I'm not going to worry so much about what the individual masses are. You can see that on a Standard Model. In fact, they actually give you the masses in units of mega electron volts per c squared, which we have seen before. That's a nice way of talking about energy, because as we know, energy and mass are very closely related. You see, this is actually defined how we've identified some of these things. For example, the up and the down quark. These have very little mass. Now, they have mass. There are many things with less mass, certainly. But the up and the down quark don't have a lot of mass. And so when we're trying to identify these items, when we're trying to identify these quarks, what we're doing typically is we're smashing some particles together. We're smashing protons together and seeing what flies out. And because the up and the down quark have so little mass, they require very little energy to be made. So we've known about the up and the down quark quite a bit. Not a problem. Very easy to get an up and a down quark to come out of a collision. To get an up quark, for example, your collision has to have an energy of 2.3 mega electron volt per c squared. That's pretty simple. So the up and the down quarks are the easy. They are also by far the most common. We'll talk about why in just a moment. But honestly, the four on the right, you're rarely going to see them hanging around for any amount of time. Most normal matter that we know of are made up of and down quarks. Proton, up, up, down. Neutron, up, down, down. Okay, these are the most common. The charm and the strange, they're in the middle. They're quite a bit more massive. Maybe even 1,000 times more. Just a charm quark is around 500 times more massive than an up quark. These have much more energy required to discover, so they are discovered much later. And because they have so much energy, because they're so massive, they want to very quickly decay. They will very quickly decay into an up or a down quark. Okay, it happens very, very quickly, and they will decay almost instantly into an up and down quark. The top and the bottom quark are huge on subatomic particle terms. They are enormous. The top and the bottom quarks have a very, very high mass, and they are incredibly unstable. You're almost never going to see them around doing anything. You may see the charm and the strange doing stuff, but the top and the bottom are so incredibly massive, anything made with a top or bottom quark is going to almost instantly decay. So mass, low mass to high mass. We don't need to worry about the individual masses. We will look at problems with masses, but in the data booklet, by the way, you probably want to have your data booklet open to topic 7.3. You're not given masses, you're not expected to know the masses. Okay? If you do look at 7.3, you can see the quarks. They have not given you the name of the quarks, they've given you the letters. U, D, C, S, T, B. Typically, that's how they'll be referred to when we're doing our Feynman diagrams next week. Okay, we have the charge. Okay, so that's the mass. We have the charge. Now, the charge is very important. Now, The charge next week, charge is one of the really important things when we're looking at a whole lot, so you really need to pay attention to this. The charge of an up is plus 2/3 E. So it is 2/3 of the elementary charge. Now, the elementary charge is the smallest amount of charge an object can possibly have. So how is it that an up quark, which is a real thing, could have a charge less than the smallest charge that anything can have? I want to give you a moment to think about that. So hopefully you're remembering that quarks are never found alone. Quarks will never ever be found alone. So while yes, an up quark is smaller in charge than the smallest possible thing to be found, you're never going to find it by itself. All charges need to be in intervals of E. So ups will never be found by themselves. In fact, everything on the top column has a charge of 2/3 E. On the bottom row, they all have negative 1/3 E. Negative 1/3 E, negative 1/3 E. And again, you can see this in your data booklet in topic 7.3. Okay. Strangeness is, like it sounds, is a strange property. There's only one particle that actually has there's only one of these quarks that has any kind of strangeness at all. I'm going to give you a moment to see if you can pick out which quark has some strangeness to it. Look hard. It's a difficult decision. Well, let's see. Is it the up? No. The up has zero strangeness. Charm? No. Top? No. Down? No. It's actually the strange quark, strangely enough. The strange quark has a strangeness of -1. Bottom is also 0, of course. And you say, Mr. Reynolds, who cares about any of this stuff? Well, you'll see why we care about this later. The strange quark will be helpful in identifying which boson mediates an interaction. Again, next week's stuff. There's another variable I just remembered probably need to talk about here, and that is the baryon number. Now remember, a baryon, if we go up top here, a baryon is a combination of quarks. It is, it's one of the combinations. And so all of these quarks we get right here have a baryon number of 1/3. 1/3, 1/3, 1/3, 1/3, 1/3. These are all the variables for 6 of the 12 quarks. 6 of the 12 quarks. You may say, Mr. Reynolds, okay, that's great. What about the other quarks? Well, in the world of particle physics, we have the normal, regular quarks and leptons. We also have the sort of mirror universe, like when everybody has goatees and is evil now. We call them anti-particles, so anti-quarks and anti-leptons. And the antis, since they live in the mirror universe, they have exactly opposite properties, except for mass. Mass still stays generally the same. So for example, an anti-up, by the way, I would write anti-up with a U with a bar on top. The bar on top indicates this is an antiparticle. So an anti-up would have a charge of -2/3 E. It would have a strangeness of 0, and it would have a baryon number of -1/3. Okay, the anti-up would just be a complete opposite from an up. Same thing goes all the way through here, including the strange quark. Indeed, the anti-strange quark has +1 as its strangeness. So these are the antiparticles. Typically, you do not write them on a standard model. You just know that if it's anti, everything's backwards. These are the quarks. Up, down, charm, strange, top, bottom. The leptons, well, actually, tell you what, while we're talking about quarks, let's talk for a moment about, let's move on to leptons, actually. So leptons are sort of similar. Leptons are sort of different from quarks. Quarks are extroverts. They always need to be found with somebody else. They can never be found alone. Leptons are basically the opposite. You will never find two leptons joining together. It doesn't happen. Leptons are always individual. We have two types of leptons, two sort of categories like we did above here. So the leptons, and this in the same mass order as before, we have the electron. That is a lepton. The muon. Do not confuse muon and meson. I can understand the confusion. I've always got to look it up myself because I always forget which one's which after not teaching it for a year. And the tau. Below that, we have the neutrinos. The electron neutrino, the muon neutrino, and the tau neutrino. Now, neutrinos are funny little particles. They have very, very little mass. They're not massless, but they have very, very little mass. But their key feature is they really do not interact with matter hardly at all. They do some, but it's very, very rare, which leads to some interesting things. I'm going to link a video in this lesson where they talk about detecting neutrinos. It's actually pretty interesting how they do it. Pay attention to when they talk about having to use old sources of oil and why that might be. It ties back to our nuclear chapter. So the electron, the muon, the tau. Now the symbols, I probably do need to draw the symbols for these. Symbols for the up, down, charm, strange, top, bottom, just the first letter, lowercase. For the electrons, all these things, we have actually special symbols. The electron is an E. Don't hurt yourself too bad on that one. Actually, I'm going to use a different color here because that may be a little confusing. Here, we'll go electron is an E. The muon is a mu. That's a Greek letter. And the tau is, strangely enough, a tau. That's another Greek letter. The neutrinos have a little Greek letter there, and we put a little E, and then a mu, and then a tau, something like that. So those are the neutrinos. Now the masses work the same way. Electron is the least mass, tau is the most. Neutrinos are really, really much less massive, like incredibly less massive than anything else. They're essentially zero mass, but way, way, way less mass. But again, the electron neutrino is the least massive of them, and the tau is also the least massive. It's not a neutrinon. I don't know what I was spelling there. Again, just like before, the muon and taus are pretty rare. They will exist and then break down very quickly, turning into an electron. We'll talk about that more next week. Now, again, talking about charge, strangeness, and baryon number, or whatever. For the charge of an electron, we know this one. It's negative 1e. And it's the negative elementary charge. We've been using that for a while. Muon, same thing. Tau, same thing. Hey, this is pretty good. Neutrinos are even easier. None of them have any charge. None of the neutrinos have any charge at all. I used the wrong color purple. I do apologize. Negative 1e and negative 1e. So the charges are a little simpler to remember than the quarks. Again, it's all found in topic 7.3. You do not need to worry about strangeness with any of these. None of these will have strangeness. So I'll just go ahead and write below here, no strangeness, even though I would say the neutrinos definitely seem strange. And instead of baryon number, none of these have a baryon number because I'll write that down here too. No baryon number. But they do have lepton numbers. Go figure, the leptons would have lepton numbers. Lepton number. And it turns out that all of these will have a lepton number of 1. Again, baryon number, lepton number, charge. Why do you need to know this stuff? You're going to see. It's going to be important next week. So we got the quarks and the leptons. Now, just like the quarks, the leptons have antiparticles. So while you have the electron, the muon, the tau, the electron neutrino, the muon neutrino, the tau neutrino, we also have the anti-electron. By the way, the anti-electron is usually called a positron. The anti-muon, the anti-tau, the anti-electron neutrino, we've seen that with beta decay. The anti-muon neutrino, and the anti-tau neutrino. Just like before, we had the ups, the downs, the charms, the stranges, and all that kind of stuff. So these are the fermions. These are the elementary particles minus the bosons. Okay. Again, there is an order to them. Be paying attention to this order. This is how they're always found. If you search for standard model on the internet, you'll see a standard model that have everything in this order. And again, on a standard model, we typically do not put the antiparticles. Real quickly, let me also put the bosons up here. Bosons are quite a bit simpler. They don't deal with charge or strangeness. Sorry, they do deal with charge, never mind. But let me just list them out because they deal with certain things. So first we have the gluon. The gluon only deals with, I'm saying deals with for now because we'll talk about what these things actually do next week, with objects, with, sorry, I'm putting dumb things. They only deal with quarks. So gluons only deal with quarks. They glue quarks together essentially. That's why they're called a gluon. A gluon is a mediator of the strong nuclear force. So whenever I talk about the strong nuclear force, which are going to be next week, we're talking about quarks held together by gluons. So the up, the down, those three quarks are held together by gluons to make a proton. The photon is a boson. The photon, which by the way we use the this little symbol here. The photon, I should probably put charge. Oh, I'll tell you, I'm just falling apart here. Let me tell you what. The charge of a gluon, let's go ahead and write it. No charge. No charge. The photon deals with items with charge. Photons can deal with things that have a charge. We know this through Coulomb's law. Coulomb's law says K(q1, q2 over r squared). So Coulomb's law says the electrical force exists between objects with charge. And of course, the photon is the mediator of the electrical force. So what are the only things in the standard model the photon will not deal with? And it is the electron neutrino, muon neutrino, and taus. Neutrinos have nothing to do with the photons, which is one of the reasons it's sometimes tough to detect them. And a photon also has no charge. I wish the store said that. Next, we have three we're sort of going to put together. The Z boson, the W plus, and the W minus boson. These deal with all particles. This is a mediator of the weak nuclear force. Again, we're going to get into what the bosons really do next week. They do have a charge. So the Z, no charge. W plus, maybe you want to guess, it is a plus 1e charge. Run out of space here. The W minus is a minus 1e charge. That's going to be really important. They will ask you questions about which one of the particles, the Z, the W plus, the W minus, we're dealing with, again, next week. There are two other bosons. These are two bosons we will not be dealing with. So I'll say two other bosons. So we have the Higgs boson. Higgs boson is obviously a very newly discovered boson. We're going to talk about it a little more next week, but this is essentially where we believe mass comes from, is dealings with the Higgs boson and the Higgs field all around us. And finally, the graviton. Graviton obviously mediates gravitational force. This has not actually been verified. Again, gravitational force is the force we know the least about. And one of the reasons is because it is so weak. And so graviton is technically not part of the standard model right now. We would never consider it because it's so weak. We would never consider it dealing with any of these things anyway. But it is a boson. We have some evidence for it, but there is no for sure anything we have right now. So it technically is not part of the standard model at the time being. But this is the standard model. Again, you can look it up on the internet and you can see examples of this, but I want you to make your own. And I want to just finish with a couple quick little things. Just finishing with a little bit of the quarks. Let me go ahead and cut the quark section out. Let's just talk about some of the things a quark can do. So I'm going to paste that down here. Paste. There we go. We're going to drag this here. Remember, we have combinations of quarks, whereas the leptons always are by themselves, the quarks are not. One of the reasons is we have a couple rules for things that exist. I mentioned this earlier. One of the rules is that the charge must be some whole number. Plus 1e, 0, minus 1e, something like that. The charge must be one whole number. So let's put here requirements for existence. We have charge equals whole number of E. So again, -1, 0, or 1. We also need a baryon number equaling whole number. So again, 0, -1, 1, whatever. And well, for now, we'll stick with these two. So the question is, what can we do? How can we make things that have a whole number of E? Well, we could have an up, a down. So an up is 2/3 E. The other up is 2/3 E. For those of you math wizards, we're up to 4/3 E. The down is a -1/3 E. Well, add those all together. Total charge of that is plus 1e, and this is actually a proton. Very, very common particle we know a lot about. We know protons do have plus 1 elementary charge, and this is what's going on with that. We could also do something like this, an up, a down, a down. So that's 2/3 E plus -1/3 E plus a -1/3 E. So it's 2/3 minus a third minus a third. Well, that's going to equal 0 charge. And so this will be a neutron. By the way, if we want to check our baryon number, we have 1/3, 1/3, 1/3. Baryon number is 1. Same thing over here. 1/3, 1/3, 1/3. Baryon number is 1. So these do exist. They work. This is where quarks can be. But we can get groups of 2 quarks as well. Now I want you to look at these quarks and see if you could figure out a combination of 2 quarks that would fulfill these 2 requirements. Put on pause and see if you can figure out a combination of 2 quarks. So you might have run into some issues because you realize that I cannot put any of those 2 things together to make a quark. It doesn't work. But you're forgetting that this is these 6 quarks are half of the quarks. There are 6 other quarks out there. So for example, we could take an up. Now an up is 2/3 E and 1/3 baryon number. And we could take a, I don't know, let's just throw in an anti-down. If I took an anti-down, the charge is, let's see, we got 1/3, but it's an anti, so it's opposite. So the charge is 1/3 E. The baryon number is 1/3, but again, we're opposite worlds, so it's -1/3. So the charge is actually plus 1, and the baryon number is 0. This is a meson. These are examples of mesons. Mesons are 2 quarks. One is a regular, one is an anti-quark. I could do an up and an anti-up. Okay, so again, we're 2/3 charge minus 2/3 charge. Baryon number, same thing, 1/3 and -1/3. And so we're going to get a situation where we have, in this case, 0 charge and 0 baryon number. Those all work. And we have a meson. So this is how we get baryons and mesons. We have to follow these rules where all particles, any freestanding particle, needs to have some whole number of elementary charges. It's got to have some whole number of baryon number. And that is always the case. That is a hard and fast rule. So hopefully this made sense. Hopefully the explanation of all these quarks and leptons and name stuff makes sense. Again, to help you sort of understand how they fit together, I want you to go on the internet. I want you to look at some standard models, and I want you to create your own. I want you to create your own standard model that will be yours next week as we go through some of this confusing stuff. I think making your own and putting some of the information that's really important on there can be helpful. So you also see spin if you look at some standard models online. We're not worrying too much about spin. That's not going to come up a ton with the kind of stuff we need to deal with, but just know that all the stuff on the left side has a spin of 1/2, and on the right side, the spins of 1. Okay. You can see in the data booklet, you can see all of this there in the data booklet. They do not tell you the, actually, no, they do. They tell you everything you basically need to know. So look there. Look at the baryons, mesons. Check some of the videos I'm going to point out. This is going to sort of start introducing you to the world that we're going to dive more deeply into on next week. So please, we'll obviously meet for a Zoom chat. Please let me know if you have any questions there. And hopefully I'm going to see some amazing standard models. I miss y'all, and I hope that hopefully we can get back together soon. And hopefully you'll have a good and safe and healthy